Now, you might think that reducing congestion is easy. In the case of cars, you just build more roads. Or in the case of the internet, you just add more bandwidth, for example, more optical fibres connecting cities. But it's not always so simple. And I'm now going to show you something very surprising. Here's an example that looks at the flow of cars along roads between 4 cities. Cars are going to try to get from city A across to city D. Now, this green road is quite a long road. It takes 6 minutes to travel from A to C, and likewise from B to D. The red road is much shorter, but it's quite narrow. The red road becomes congested. So the time it takes to travel along one of the red roads is equal to the number of cars that are using that road. And then finally we have this yellow road, which is a very fast road. It only takes a minute to travel along the yellow road. Okay, let's see what happens if 4 cars try to get from A across to D. Let's see which route they take. Well, the first car wants to go from A to B along this road. That just takes 1 minute. Up the yellow road, which takes a minute, and along the second red road. That takes a minute. So that's 3 minutes in total. What about the next car? Well, the next car wants to follow the same route, but now, of course, this takes 2 minutes for each of those cars because that road is congested. A minute up here and another 2 minutes along there. And likewise with the third and fourth cars, they also prefer to take this same route. So here they are, going along the red road, across the yellow road, and along the second red road. So how long is this taking the drivers? Well, it takes 4 minutes now to go along a red road because there are 4 cars. Remember, this road is congested. It always takes a minute to go along the yellow road and another 4 minutes along this red road. So that's 4 plus 1 plus 4 is 9 minutes. Now, would any of those drivers like to switch and take a different route? Well, let's have a look. Well, one possibility is to go along here and then this way. That would take 6 minutes plus another 4 minutes, which is 10 minutes. So that's longer, so the drivers don't want to do that. The only other route that a driver could take would be to go up the green road, down the yellow road, and along the other green road, and that would be 6 plus 1 plus 6, which is 13 minutes, which is even longer. So none of the drivers want to go any different route. Now, this yellow road is a very fast road, so obviously it must be helping with the traffic flow. Or is it? I'm now going to show you a very strange effect. It's called Bray's paradox. And to help understand it, I have a physical model of Bray's paradox here. So what we have is a weight that's suspended from some coloured strings from the ceiling. And these are just like the roads. So this red string is an elastic string. That's like the red congested road. And this green string is not elastic. That's like one of the green roads. And then here we have a very short piece of yellow string. That corresponds to the yellow road. And then the second red and green roads are up there at the top. Now you'll notice that these green strings are not under any tension. They're completely slack. And at the bottom there, we also have a scale which is telling us how many minutes it takes to travel between those two cities. So at the moment it says 9 minutes. Okay, let's see what would happen if we removed that yellow road. So I have a pair of scissors, and what do you think is going to happen when I cut this yellow cord which is holding up the weight? Any ideas? What's going to happen? What do you think is going to happen? You think it'll go down more? Okay, let's cut the yellow string and see what happens. Okay, well, very surprisingly, the weight's actually moved up, which means that this journey time has reduced down to about 8 minutes. So that suggests, going back to our roads, that if we remove the yellow road, it might actually improve the traffic flow. Well, let's have a look and see what happens if we remove that yellow road. So let's take these cars off and let's work out which way they're going to go. So now there are only 2 routes to get from A to D. So the first car, it doesn't matter which way they go. Let's just assume they go along the top here. The second car wants to avoid congestion on this road. So the second car is going to take the bottom route along there and then along there. The third car, again, it's both the same. They could go either way. Let's assume they go along the top there and along that red road. And the fourth car, again, wants to avoid congestion on this road, so they'll take the bottom route. So they go along there and then along there. Now let's have a look at how long it takes these drivers to get from A to D. Well, they each take 6 minutes plus 2 minutes, which is 8 minutes. So that's less time than it took when the yellow road was present. This is a very strange effect, and it arises because these drivers are acting selfishly. They ignore any benefit which their decisions might have for other drivers. And this strange effect can actually happen in real life. In Seoul, in Korea, when they closed one of the 3 tunnels through the city, they actually found that the traffic flow improved. Now, on the internet, the packets of data are like the cars, and the connections between the computers are like the roads. And again, there's no central controller on the internet, which means similar paradoxes to this can arise there as well. So one way to help congestion would be to try to find a way to coordinate the flow of data on the internet. But can we find other ways to reduce congestion? Well, on the roads, one way to reduce congestion is to reduce the number of cars. And we can do that by having more than one person share the same car. I'm going to show you how we can use a similar idea on the internet. So let's imagine we want to download a big file like a movie. Well, we first of all have to break it into manageable sized chunks. And for simplicity, let's imagine that our movie has just 2 chunks, corresponding to the hare and the tortoise. Now, the computer that sends out the movie is called a server. And it could send out these 2 chunks to you, and then to you, and then to you, and so on. But that would take a very long time. And the more people who wanted the movie, the longer it would take. So instead, the server could send the movie chunks to you and send them to you, and then you could pass them on to your friends, and your friends could pass them on to their friends. And that's called peer-to-peer distribution. But now we have a different problem. If you've ever tried to collect sets of cards or sets of coupons, you'll know that it's very easy to get started, but it's really frustrating to get those last few pieces. I'm now going to show you a really clever way to solve this. Now, when you arrived, you all picked a red envelope at random out of a box. I'd like you to open that now. And half of you will find in that envelope the image of the hare, and the other half of you will find the image of the tortoise. So each of you has got half of the movie, and your job is to get the other half. Okay, let's suppose that I'm one of these computers sending out this movie, and let's suppose that I've already got the hare and the tortoise. What piece should I send to you? Well, if I send the hare, then those of you who've already got the hare will get a duplicate, and you still won't have the complete movie. And also, if I sent out the tortoise, those of you who've already got the tortoise would get the same piece twice, and you'll still be missing the other half of the movie. Of course, you could each tell me individually which piece you're missing, and I could just send you that. But that would mean a lot of messages went backwards and forwards. That would take a long time. There's a much cleverer solution, and it's this. I have here a special image that's constructed from the hare image and the tortoise image. What I'm going to do now is to take this image and to overlay it on the images that we have. So there's an image of the hare. When I overlay this image, it becomes an image of a tortoise. And if I take this image and instead I overlay it on the image of the tortoise, what I get is an image of the hare. Now, when you came in, you should also have got another envelope, a green envelope, and if you open that, they're all the same. They all have this special image in them. So if you take your 2 images and place one on top of the other, and you look up at this white screen here, you should be able to see that same effect. Now, remarkably, we can extend this idea to an infinite variety of chunks, so that there are no 2 that are ever the same. So if a real movie, for example, had 1,000 chunks, then any 1,000 chunks would give you the original movie, and you'd be guaranteed never to be stuck with duplicates. This means we can avoid sending repeated information, and therefore we can reduce congestion. Okay, let's go and take a look at Andy's video, which should have finished downloading.
You'll never guess what. Chris has got a secret hiding place. He didn't know I was watching, but I saw him hiding something. It's in the cabinet with the light box on it.
Okay, my secret has been revealed. Before I tell you what the surprise is, though, what I'd like to do is just to ask you to imagine a different kind of web. A web in which you could ask your computer any question you like, and it would go and trawl through all the web pages and find out information, analyse them, combine them together, and then answer your question. Now, of course, that would require computers which are much more intelligent. In the final lecture, we look at how scientists are trying to build intelligent machines by allowing them to learn from themselves. Okay, my secret's been revealed, so I suppose I'd better share this with you all tonight. And it is a big bag of sweets. Okay, thank you all very much.